So I want to focus in this video about the importance of the ratio of saturated fat to monounsaturated fat. In the video, How Olive Oil Makes You Fat, I showed this experiment in rats where they fed the rats different diets, either high in olive oil, monounsaturated fat, high in sunflower oil, polyunsaturated fat, or beef tallow, very high in saturated fat. And palm oil is sort of similar to beef tallow, but less high in saturated fat than the beef tallow was. The lipogenic enzymes are massively upregulated. As you can see, we're looking at an enzyme called ACC. In the rats fed olive oil, their level of ACC was 15.4, which is more than double that of rats fed beef tallow, where their lipogenic enzyme was less than half of that. What I said in that video is that oleic acid drives the production of lipogenic enzymes. In the rats fed beef tallow or palm oil, those diets are actually relatively high in monounsaturated fat. You can see I've got beef tallow highlighted here, and that diet is almost 40% monounsaturated fat, but yet the beef tallow fed rats have significantly low lipogenic enzyme expression, and you can see that they have about 1.5 times as much saturated fat as they have monounsaturated fat, and that matters, and I'm going to focus in this video on that ratio of saturated fat to monounsaturated fat, why it's important. You can see the palm oil fed rats have a little bit lower. Their ratio of saturated to monounsaturated fat is 1.2 to 1, and their lipogenic enzyme expression is a little higher. Then we go over to olive oil, and I'm skipping soybean oil for the moment because since that's all polyunsaturated fat, it's kind of a whole different kettle of fish. So the olive oil diet, their ratio of saturated to monounsaturated is only 0.2 to 1. So you got 5 times as much monounsaturated fat, and as you can see, the lipogenic enzyme expression is way up. This is in obese humans. So this is a very interesting study. They're looking at the free fatty acids, and this is increasing BMI on the bottom. And you can see that this line representing oleic acid, monounsaturated fat, is increasing. So the free fatty acids, those are when your fat cells release fat to sort of feed the rest of your tissues. The free fatty acids are what's in your blood that the other cells can take up and burn. And so what you see is that as obesity increases, the availability of oleic acid, monounsaturated fat, steadily increases in the free fatty acids. And those free fatty acids are really where the rubber hits the road. That's what your cells are going to take up and feed the mitochondria with. And this is, again, in humans. This is in human muscle tissue. And what you see is this enzyme called SCD or SCD1. What it does is it turns your saturated fat into monounsaturated fat. So it turns stearic acid into oleic acid. And what you see is the higher your body mass index is, the more obese you are, the more of that SCD1 you have in your muscle cells. And that means the higher your muscle cells will be in oleic acid. And so in that same study, they took muscle tissue from either obese or lean humans. And what they showed is that the obese humans, their muscle tissue is indeed full of oleic acid, monounsaturated fat. And this is even more, I said the free fatty acids were where the rubber hits the road. Acyl carnitines, when you burn fat and it actually goes into the mitochondria, you take it off of the glycerol and you stick it onto carnitine, making an acyl carnitine. And so acyl carnitine is literally the fuel that's being sent into the furnace. This is truly where the rubber hits the road because, of course, muscle cells can take free fatty acids out of the bloodstream, or they can take fat that's stored within the fat cell and burn that. So they have options about where they're getting their fuel from. And this is the actual fuel in the mitochondria. And you can see here's linoleic acid, that's PUFA. Here's saturated fats. None of them are different except oleic acid, the high monounsaturated fat content of the fuel in the fire of the muscle fibers of obese humans is specifically high in oleic acid, which is the main component of olive oil. In that muscle tissue of obese humans, when they bring in fat, they're much less likely to burn it, and they're much more likely to use it to make triglycerides, which means they're much more likely to store it. Why? It's because lipogenic enzymes are increased. And so this is the most interesting part of that study. what they did was they took muscle tissue from lean humans and they inserted the SCD1 gene into it. And so what that does is you take that lean tissue and you convert more of the saturated fat into monounsaturated fat. And so what happens in those tissues is, you can see here, this is fat oxidation. This is burning fat. If you have more oleic acid in that tissue, you burn less fat. And this is storing fat. Esterification, that means storing fat. And this is in your triglycerides. So if you make more oleic acid, you store more fat and you burn less fat. But this graph is really interesting. So just increasing SCD1 expression, and the only thing that SCD1 does, as far as we know, is convert saturated fat to monounsaturated fat. And if you get more monounsaturated fat into human muscle tissue, you more than double lipogenic enzyme expression. And the reason that I focused on ACC in those rats that were eating olive oil is this is the exact same gene, and this is in the muscle tissue of obese humans that have high expression of the enzyme that makes monounsaturated fat. So whether or not you're a rat that's eating oleic acid, or you're a human who has an enzyme that produces oleic acid, either way, you increase lipogenic enzyme expression. And so this is a summary. If you go back and watch how olive oil makes you fat, I have a more detailed version of this. If you're really interested in molecular biology, I'm going to kind of blast through it here. When you eat dietary oleic acid, your gut produces something called OEA, which activates PPAR alpha, which upregulates D5D and D6D. Those enzymes convert linoleic acid to something called arachidonic acid, and then the ARA hydrocarbon receptor makes something called an enzyme called CYP1B1, and those things produce a molecule from the linoleic acid in your diet, ultimately called 15-HEAT. And that 15-HEAT activates a thing called PPAR gamma, which activates another thing called SREB-P1C, and that directly upregulates the lipogenic enzymes. And so this process, of course, uses both monounsaturated fat and polyunsaturated fat. And so we can say that oleic acid is involved in lipogenic enzyme expression by increasing D6D and D5D, but there is a catch. And here's the catch. And this is why that ratio of saturated fat to monounsaturated fat really matters, because PPAR gamma and SREB-P1C are only activated when they're acetylated. Furthermore, D6D and D5D, the enzymes that convert linoleic acid to arachidonic acid, are driven by the NADH to NAD plus ratio. Having a high NADH to NAD plus ratio and having acetylated enzymes are both associated with something called reductive stress. And I know that's an annoying word, and I have a better way to talk about it that we'll see coming up. These are the papers that prove what I just said. They're boring. I'm not going to get into it. And here's the thing. So context matters. So lipogenic enzyme upregulation by dietary oleic acid or by SCD1 is dependent on the NADH to NAD plus ratio. So you need both. You need PPAR alpha activation, and you need high NADH to NAD+. This is another paper by James Natambi. This is really fascinating. So this is in mice, and what they're looking at is the NAD. This time the ratio is upside down. It's the NAD plus to NADH ratio. It can be written either way. Sort of annoying, but that's what it is. And so in this case, we want the ratio to be high. That means there's lots of NAD plus and there's not too much NADH. And so what happens is you can see this one that has massive amounts of NAD+. Well, those are mice that don't have the gene SCD1, so they can't convert their saturated fat to monounsaturated fat. And that means they wind up with this huge amount of NAD+, which is great. Those mice are hypermetabolic. They have a super high metabolic rate, and they never get fat. And that's great for them. And that is just because they can't produce oleic acid. And in this chow diet here, there's almost no oleic acid in that that food is mostly starch. There's no oleic acid there. So they can't make oleic acid. There's no oleic acid in their diet. They have a huge metabolic rate, tons of NAD+. They never get fat. Now, look what happens if we take those same mice and we feed them a diet over here. And this is actually from another paper. They didn't give us the exact saturated fat, monounsaturated fat, but the diet is this. This is taken from another paper, and they're using the same thing, which is a diet of mainly lard with a little bit of soybean oil in it. You can see those right here. And so this diet winds up being a ton of monounsaturated fat, quite a bit of polyunsaturated fat, and you can see the ratio of saturated fat to monounsaturated fat is below 1. And so remember that first chart I showed with the rats, when we went to palm oil, it was 1.2 to 1. The lipogenic enzymes start to increase. Well, this is all the way down to 0.8 to 1. And you also have quite a bit of PUFA coming in. And so what happens is the amount of NAD plus compared to NADH just plunges. So, right. So now we're giving them a lot of oleic acid in their diet, and that reduces NAD plus and it increases NADH. That starts to put them into reductive stress. And then in this last group, what happened is they into the muscles of those mice, they're actually made this thing that expresses extra SCD1, right? So now these guys are making tons of SCD1 in their muscle tissue. They're going to have tons of oleic acid in there. And look what happens to the NAD+. The levels drop. And even the mice on the high starch, low MUFA diet, their NAD plus to NADH ratio is less than half of a normal mouse. And this is in the muscle tissue. And it's just because they have more oleic acid. So oleic acid causes reductive stress. There's no doubt about it. And reductive stress activates lipogenesis. The lipogenic enzyme, ACC, was either increased by dietary oleic acid, that's olive oil fed rats, or by oleic acid in human muscle tissue by overexpressing SCD1. So no matter how the oleic acid gets into the organism, whether it's through the diet or from enzymes, you increase lipogenic enzyme expression. Here's perhaps a better way to think about reductive stress. This is a paper about pseudohypoxia in late-stage diabetes. Let's say you're having a heart attack. Blood flow is stopped to the heart. What happens is you end up with a very high NADH to NAD plus ratio. Lack of oxygen causes a high NADH to NAD plus ratio. So they call it pseudohypoxia because there's plenty of oxygen around, but you're not burning it in the case of diabetes or in the case of having high oleic acid in your tissues. The reason for that is this is the electron transport chain. This is how we make ATP over here at complex 5. NADH gives its electrons to complex 1, and that converts it back to NAD+, which is what we want. We want a lot of NAD+ and not so much NADH. And those electrons come down here. They go through complex 3 and they go through complex 4. And complex 4 is actually, that's how we burn oxygen normally in the production of ATP. So you see oxygen here is becoming water at complex 4. So if you don't have oxygen, NADH builds up because there's no oxygen here and the electrons can't flow back down through 4 because there's nowhere for them to go. The other thing in this chart to see is that sometimes the electrons, if there's too many electrons coming in through both complex 1 and complex 2, you can see this Q. This can be a bit of a bottleneck, and what happens is the electrons bounce back out over here and they create this thing called superoxide, which is O2 minus, which is oxygen that's picked up an extra electron, and you can see that becomes hydrogen peroxide. It ultimately becomes water. And so we have two ways of burning oxygen. One is through making ATP, and the other one is through superoxide production. So here we go. This is just another view of the electron transport chain. And I drew that bottleneck again here. So complex 1 and complex 2, that's succinate dehydrogenase, are both trying to give electrons to Q. And if that gets overwhelmed and bottlenecked, the electrons come back out right here, and you can see that superoxide. And this is all dependent on succinate dehydrogenase activity. That's complex 2 drives most of the superoxide production. Now the superoxide is just harmlessly reduced to water by your antioxidant system. 99.9% of it is. So it is a reactive oxygen species. It is a free radical, but 99.9% of the time, it's not a big deal. Here's really the magic. This is how this works. So you've got NADH here, and this thing that I call complex 6, but it's more commonly known as NNT. This takes these electrons from NADH and it transfers them to NADP plus, which makes the reduced form of NADP, which is NADPH. Reduced things are the ones that have the electrons at the moment. And so NADPH is the reduced form, and NADH becomes NAD plus when it gives the electrons to NADP plus. So that's great. And then those electrons are used by your antioxidant system to reduce glutathione. And then the reduced glutathione, again by your antioxidant system, those electrons are used to fully reduce superoxide all the way back to water. So water is fully reduced superoxide, and it takes electrons to do that, and taking electrons replaces NAD+. So superoxide production burns oxygen. Superoxide prevents pseudohypoxia. And oleic acid, the difference between unsaturated fats and saturated fats is that unsaturated fats have less input at complex 2, less input at succinate dehydrogenase. And so oleic acid doesn't have as many inputs here. That means there's not as much hydrogen peroxide produced. And if there's not enough hydrogen peroxide, there's nowhere for the electrons from NADH to go, because ultimately these electrons flow back to reduce hydrogen peroxide. And so succinate, that succinate dehydrogenase, complex 2, replaces the complex 2 inputs that are removed by SCD1 when it converts your saturated fats to oleic acid. And so I just started selling these disodium succinate capsules at fireinabottle.net/shop. I'm super excited about them. I've only had them for about 2 weeks. I've been experimenting. Results are good. Unfortunately, like a week into the experiment, I got this flu. You can hear my voice is scratchy. I've had zero digestive upset from this, and I found I can take 6 or 8 capsules at a time. This is the citric acid cycle. You can see that succinate dehydrogenase, that's complex 2. That is the FAD input that helps drive superoxide production and helps you replace what is lost by the actions of SCD1. So disodium succinate hasn't been trialed in humans yet in a controlled trial, but this is what happens when you give it to mice. So these mice were given 2% of their diet as disodium succinate, and they're on a high-fat diet, and you can see the mice that didn't get the succinate gained 8% of their body weight over 4 weeks. The ones given 2% of their calories, so that would be something like 10 to 15 grams a day in a human, they lost about 3% of their body, well, maybe 4% of their body weight. The mice given succinate on a high oleic acid diet also have excellent glycemic control. This is another paper. You can see the succinate absolutely increases oxygen consumption. So this VO2, that means volume of oxygen that they're burning. And you can see this blue line are the ones given the succinate, and it's consistently throughout the day, especially at night when the mice are active. You can see they're absolutely consuming more oxygen while they're awake and eating that succinate. The succinate in this study also prevented weight gain, as you can see. This is a third study. In this study, they actually looked directly at NADH to NAD plus ratio. You saw in those mice how feeding them a diet high in oleic acid and linoleic acid dramatically increased the NADH to NAD plus ratio. Succinate does the exact opposite thing as oleic acid. I don't know if I've seen any other intervention that affects the NADH to NAD plus ratio this dramatically. And you can see those mice also are stronger. They have more grip strength. And this is immediately. This is only 30 minutes after a succinate injection. They have higher grip strength. They're stronger. Okay, that's all I've got for this video. I'm having a lot of fun with these oleic acid videos. Oleic acid absolutely increases lipogenic enzyme expression. It does that by activating D6D and D5D, but it also does that by creating a hypoxic situation because you're not producing superoxide when you're burning fat. Succinate is solid oxygen. It will eliminate the hypoxia created by oleic acid.
I'm Brad Marshall, author of the blog FireInABottle.net. You can join the discussion on Reddit at r/saturatedfat. Follow me on Twitter at @fire_bottle or on Instagram fire_in a bottle. Thanks for watching.